when we go back to our structure, so the question that was raised was, if we bias this, if we apply voltages at the corresponding terminals, for example, if I apply, let's say this is a body, this is N type, and let's say the batteries are connected in this fashion. Okay, and let's for the moment assume that these two are shorted and maybe connected to some other voltage. The question that is raised is, we said that the mobile charges that we'll see here, right? So this is P plus, this is P plus. We'll see holes here. So the mobile charges that we'll see here, we said that this is Q mobile is equal to Cox times W times L, then VSG minus threshold voltage of P, right? So if I understand correctly, you are asking, why do I have this negative P threshold voltage, or? Okay, good question. So her question is, why this expression alludes to only mobile charges, because we also have immobile charges in the channel, right? So for example, we have positive charges also, which came when all the, negative type trivalent impurities got rid of their, sorry, this is N type, right? So the pentavalent impurities got rid of their positive charges, got rid of the electrons. So essentially we had Nd plus. We had, forget about the D part. D is essentially because we call it the donor, but the key thing is that we have positive fixed impurities there. So why do we have, why does this expression allude to only mobile charges? So the reason it alludes to the mobile charges is the following. So when let's say we didn't have any holes, right? We are not in that regime where we still have mobile holes, but we still have electric field. So we still have electric field. So what is the purpose of what is this electric field doing? This electric field is essentially getting terminated on these Nd plus fixed charges, right? So on top of this, so you need to apply a certain amount of electric field before which the mobile charges will start appearing, right? So that mobile charge, that threshold voltage, the critical voltage, we are encompassing that entire physics into saying that VTHP is that threshold voltage. So anything we apply on top of this is only going to add incrementally to the mobile charges, right? So this is the total voltage. We are subtracting that amount of critical voltage that is required to support only the immobile charges. If I subtract this, whatever is remaining is only the mobile charges. Yes, that's what it means. That's correct. So we can in fact say that immobile charges is equal to COL times WL times threshold voltage, right? So that is an approximate back of the hand calculation, and it's not very bad, right? Okay.
So but the mobile charges are getting generated even when there were just the mobile charges, there were mobile charges.
Correct, right. So his point is that mobile charges are getting generated continuously. So in principle, if you put it under a microscope, you will never see that it is always devoid of any mobile charges. There is always some concentration of mobile charges. But what we are essentially saying that, is it high enough to cause significant amount of current? Right? It's never zero, right? So that's why there is another term for this. So when you hit this threshold voltage, right, it's not like below threshold voltage your mobile charges are zero and suddenly they are like abruptly they have come, right? So the technical term for threshold voltage is, it is that voltage for which the concentration of mobile charges in the channel is equal to the concentration of N type charges in the bulk. So essentially this channel has become as much p-type as the bulk is n-type. Right, so that is the technical device level definition of a threshold voltage. Right, so again, to drive home the point, it's not as if you are doing a device physics course, you cannot really say that below threshold voltage there is no mobile charges, and above threshold voltage you have lots of mobile charges. It's always a gradient. But in this course, we are not particularly bothered with that gradient. What we are bothered about is that if we have sufficient amount of charges, what can I do with it? So we need some way of figuring out what are the guiding principles or what are the guiding equations, if we may, which will help us in getting us the current voltage characteristics under the influence of some voltages between terminals. Okay, make sense? Okay. So when we stopped in the previous class, we saw that we had developed some current voltage equations between the source and the drain, and we saw that this was the equation that we stopped at. So this part of the equation we had derived, and then I put in a fudge factor and said that if you have you now apply, this is source, this is drain, and if you apply a battery between the source and the drain, and assuming that there is a battery that has been connected between the gate and the source, which has given rise to mobile charges here, and the concentration of mobile charges under the assumption that the drain and source are same voltages will have a profile of a rectangular slab, right? Because there is no way you can identify which side is source, which side is drain, because geometrically also they are same, electrically this device is identical. Then we said that now if I apply a small VSD, right, and we went from first principles and said that this will be the current voltage equation. But what I essentially didn't allude to is the fact that if I apply a VSD, this rectangular profile that we have will also not remain rectangular. If it remains rectangular, then yes, then the expression inside the box holds. But if I apply VSD, there will be some electric field inside the channel going from one side to another, which means there will be a gradient of potential in the channel from one side to another. Then we said that if I look at this continuous this continuous box as a sliver of MOSFETs connected adjacent to each other, then we saw that the amount of mobile charges under each of those small MOSFETs will also vary, because essentially the gradient of voltage has changed, right? So which means that the assumption that we started off with was not particularly valid, right? The assumption that we started off with, that it is a rectangular slab of charges, that is mobile charges, that remains, and that becomes invalid. So naturally the expression for current that we came up with will also change. Then I said that, so now as we can see that if I apply VSD, the amount of charge, mobile charge that we will see in the channel will decrease. So which means it is expected that the current will also decrease. And then I added this factor of minus half VSD squared, right? So that gives us, I mean, if you do if you pick up any standard circuit theory textbooks also, you'll find the derivation. But the intuition is ultimately the amount of charges that are getting mobilized under the influence of electric field has reduced, hence the current has reduced. Okay, so having said that, this expression is still valid as long as we maintain VSD is much small, which essentially means that much smaller than what? Which means what this term will be essentially valid when the first term is much larger than the second term, right? So under those term is much larger than second term, under that condition of VSD, you can still approximate the current voltage equation as a stuff when we have only rectangular like charge profile in the channel. Okay, so before we move forward, one interesting anecdote. So let's assume that still this is our ISD is this, right? If we still assume that it's a rectangular profile, so our ISD remains this. Okay. So now, can you comment on what this device looks like if I vary the VSD voltage and I observe this current ISD? So let's say this part is a black box, or a blue box in this case. If I apply this, if I change this voltage VSD, this battery voltage, and if I observe ISD, what will be my conclusion? What type of device exists inside the box? It's a resistor, right? Now, if I know that, let's say another terminal comes out of this box, which controls this VSG, right? So I can then say that I can control the value of the resistance by changing VSG, right? So this essentially becomes a voltage variable resistor. You don't have to pluck out a resistor as you do if you have to change in a breadboard, for example. You targeted 1 kilo ohm, maybe it's 2 kilo ohm, so you have to pluck it out and then put another 1 kilo ohm back. You don't have to do that here, right? You can simply change VSG to change the value of the resistor. An interesting thing is that the terminal which is controlling the resistance is not the same terminal between which you are applying the original battery. It's some other terminal. It's the third terminal that is changing the value of the resistance, right? So that's why it's called a trans resistor. And the name of the transistor came from this effect, that this is a trans resistor. Okay, so that's an interesting historical anecdote that you might find interesting. Okay, so now we still want to, going back to previous class, what did we do? We essentially plotted the Y21 and Y22 parameters. And if we concentrate on the Y22 parameter, we are plotting ISD with respect to VSD, and the equation is now so what did we see? If we when VSD is much smaller than is small enough so that I can neglect the half VSD square term, then essentially this is a straight line. And when the minus half VSD square terms will start kicking in, this will start to flatten. And that is good. That is good because ultimately our aim is to get Y22 to be 0, right? Which essentially means that we would want the ISD versus VSD plot to be as flat as possible. Okay, so it looks like it is flattening. So can you comment on when this is flattening, what is happening to the channel charge? So let me draw the cross section again. So I'm not sketching the gate voltage because it is assumed that the gate voltage is fixed and it has been applied. So it has been applied so that the channel charge is present. So initially the channel charge was flat. Then I am applying a battery between the source and the drain. So the channel charge has become slightly trapezoidal, right? So this is H plus. These are all mobile charges I'm drawing. I'm not sketching the fixed charges underneath. So can you comment what happens if I keep on increasing VSD? Because looks like if I keep increasing VSD, the rate at which the current would have decreased is not the same anymore, right? Because of this minus half VSD squared term. So what does this imply with respect to what's happening in the channel? Mobile charges are decreasing. In fact, that is correct, but is it decreasing the same way as it is decreasing towards the drain and the source side, or there is a preference? Excellent, right? It will decrease more towards the drain side, which essentially means that the profile will start. So let me also mark these out. You have plenty of holes in these tubs. So essentially you have something like this. And now if I keep on increasing VSD, so this will become like this will become like this, and that's all that's going to happen. Okay. So as you see what's happening here is if I keep on increasing VSD, so here if I say what, can you comment on what is happening when, let's say your V, so it looks like I can, if I keep on increasing VSD in this case, what happens when VSG minus threshold voltage is exactly equal to VSD? And here I would like to draw your attention to what is happening at this junction. Something very interesting happens at this junction when this condition, you reach this condition. Think in terms of what is happening to the concentration of mobile charges just at the junction of the drain. It is decreasing, but something critical is happening. Yeah, right. So essentially, if I zoom in here, so let's say I zoom in here and I only concentrate on this sliver of MOSFET that exists just at that junction, then what do I see? What is the voltage difference between this guy, right? So let's say this is, let me put some numbers, for example. So let's say source voltage is 3 volt, drain voltage is 1 volt. Gate voltage, let's say, is 0 volt. Okay. And let's say the threshold voltage is 0.5 volt. Okay. So can you comment on the difference of when we have connected it like whatever I have shown here? Can you comment? Do we have mobile charges in the channel? We have, because in that, when I say in the channel, in this context, I mean just at the drain junction. So at the drain junction, that small sliver of MOSFET is seeing a voltage of 1 volt between the gate and the channel, right? So this is 0, this is 1, right? I'm only concentrating in this box here. And the threshold voltage is 0.5 volt, which means I'm half a volt above whatever I require. I'll be having mobile charges. Okay. So now let's say I increase VSD. When I increase VSD in this context, I assume that I have kept the source same. I'm decreasing the value of the drain. Okay. So let's say I decrease it to 0.5 volt. So now can you comment whether I will be having mobile charges just at that junction? What will be the difference? What is VSG rather, or yeah, what is the difference between the gate voltage and the channel voltage just at that junction? Maybe I'm confusing you. So let me break it down even further. So this voltage is 0, it's not changing. What am I doing? I'm changing this voltage, right? This H plus is, assume that's like a filled with holes. There is no voltage drop across H plus. So whatever I apply at this terminal also appears at the junction. Okay, so if that is the case, if I apply 0.5 here, what appears here? 0.5. So what is the VSG? 0.5. What is the minimum VSG that is required to generate threshold voltage, generate mobile charges? 0.5, right? So essentially, we are now at the critical voltage where you cannot have any mobile charges at all, right? So if you keep, the moral of the story is if you keep on increasing VSD, right? If you keep on increasing VSD, there is the channel profile will from becoming a trapezoid will go towards almost a triangle. And at the edge of the triangle, where almost the triangle is getting intersected here, you are not going to have any mobile charges, right? So the current at that particular the value of the current at that particular condition is a very critical value of current. So let's find that value first, and then I will comment on exactly what happens if I keep on increasing VSD beyond that. So ISD when VSG is equal to VSD plus threshold voltage, or let me write it like this. So if I replace VSD with VSG minus threshold voltage, I will get this. It will be half mu P Cox W over L VSG minus threshold voltage whole square, right? Half of it goes off, and essentially it's a replacement of variables. Okay, so now the reason this is profound is because of this. So now intuitively, can you comment what will happen if I keep dropping this drain voltage further? It was 0.5, I go to 0.4, 0.3 to the channel charge profile. It looks like it is going to change, but how will it change? The distribution seems to be ending before some distance. So what she is pointing out is, it seems like now we are going to have something like this or something like this and so on. Is this what you are trying to say? Yes, in fact, it does that, but that is a second order effect. We'll come to that later. So for the time being, let's assume that, okay, let's concentrate on what happens if that happens, right? So let's assume that distribution ends before some distance. So then what is happening in this region? What is happening in this region? No mobile charges, but what we have these plus charges, immobile plus charges. So that region is highly resistive, right? You don't have, I mean, the fact that it is a conductor in the channel was because we had mobile charges, right? If we get rid of the mobile charges, then that region becomes highly resistive. So essentially, whatever increment of drain to source voltage or source to drain voltage we will be applying, the extra voltage will essentially drop across that sliver where you don't have any mobile charges, right? It is almost equivalent to saying this is what is happening, right? So if you, it's like, let's say I have a current source, and let's say this is the R channel, which is filled with mobile charges. And if we keep on increasing the current source value, so some voltage will drop across this R channel. But if I keep increasing the difference between the threshold voltage, I mean, keep going into this region where the channel has almost been cut off, then essentially this model is not valid anymore. There will be another model which will give rise to some R due to immobile charges. Right? So the extra drop, in this case, I have shown with respect to a current source, but if we apply a voltage source, that extra drop will accrue on that immobile part of the channel. And because that extra drop will accrue on the immobile part of the channel, that extra voltage drop, the amount of channel that will shift will be very small, because with even a small amount of shift, you will be able to accommodate for that extra drop. So for all practical purposes, you will not see any shift of this triangular profile. So essentially what I'm saying is that in order to understand what's going to happen if I keep increasing VSD, you will have to zoom in to a large extent to understand what is happening at that channel, at that edge. And that becomes a second order effect. There will be some change, but that change is essentially negligible. So if that change is negligible, what am I essentially saying? I'm essentially saying is that the triangular charge profile that you see will get fixed. Even if you keep on increasing VSD, the triangular charge profile will not change. And if the triangular charge profile does not change, what happens to the current? The profile of the charge is not changing. So can you comment what will happen to the current? Will the current change? Current go to zero? Current goes to very high value? It remains constant? What happens? It will remain constant, right? So essentially what is happening is now, if you see, if I reach this critical voltage where I satisfy this condition, that triangular profile of charge is no longer getting affected. Because it is no longer getting affected, you are not able to change current anymore. You can keep on increasing VSD, but your current is getting saturated. Right? Since your current is getting saturated, this region of operation is called saturation region of operation. Okay, and your current will get saturated to the value whose expression is this. And if I plot the same thing on the ID/VDS characteristics, what am I going to see? I'm going to see that at that value of VSD, where I have this saturation, beyond that, the current will become constant. Okay, and this value of constant is, the expression for this constant current is half mu P Cox W over L VSG minus threshold voltage whole square. And that value at which, the value of VSD at which this has happened, this will be equal to VSG minus the threshold voltage. Okay. Does that make sense? So from a circuit designer's point of view, right? So I mean, we are essentially trying to get into a zone where I don't have to think about what is happening inside the device, right? So more and more we get into more and more we are trying to get into this IV characteristics, is because we don't want to look into what is happening to the hole density, current density, hole density and charge density inside. Right? We want to get rid of that picture and get everything in the IV characteristics domain. Essentially, we are trying to get into the plot domain, so that I don't have to go into the device every time. Because the moment you go into the device every time, you are essentially taking time out from analyzing circuits, right? So essentially, we are trying to get into all IV characteristics domain. And now you see that we are in that domain where we are probably equipped enough to get all the 4 IV characteristics, because I1 V1 and I1 V2 we got simply because they are all 0, right? We didn't have the I2 V2 or I2 V1 characteristics. So we got from the last class and part of this class, it seems like we are now in a position to characterize the current voltage condition of the entire MOSFET for all 4 quadrants of I and V. Okay, so if we do that, then we can then say that here MOSFET is an abstraction, that symbol of abstraction of the device, and then we can run with it. Okay, so that's all we are trying to do here. So if we are convinced with this, so what is the let's close the discussion. Let's close the discussion with finding out all the Y parameters that corresponds to this particular device. Okay, so our I1, which is equal to IG, is essentially always 0. We do not have to bother about it. So let me also sketch the device. This is source, this is drain, this is gate. Our I2, which is ISD, is equal to, it has primarily 3 regions of operation, but the cutoff region I am not particularly bothered about, but let's write it out anyway. Yes.
Why does the fixed charge profile imply the charge?
Okay, so his question is, why does the fixed charge profile imply the current is fixed? So let's maybe spend a couple of minutes here. So why was the current changing to, I mean, if you recall, when you had this rectangular slab, right? And then we said that when you are when we were applying some VSD, right? So the charge profile was changing, right? So essentially, what is current? The current is, very crudely, the current is what is the amount of time this total amount of charge is taking to move from this side to this side. Correct? So if the total amount of charge is changing, then current will also change. If the total amount of mobile charge is not changing, then the current will not change.
In that case, the profile remains same regardless when we change VSD.
Right. So now the profile will remain same. Because the profile will remain same, the current will not change. Right. So when we were going from, for example, when we didn't have, let's say we had only this type of profile, right? So if I apply VSD, this profile is changing. This profile is going from there to here, right? So because the profile is changing, you are going to see a change in current also.
So let's say the Q mobile remains constant after the triangular line.
Right. Yes, it is in fact constant. Yes.
Transit time changes when we change VSD, right?
Transit time doesn't change. Why do you say transit time is changing?
Because the potential we have applied.
Correct, right? So yeah, very good point. So his point is this. So basically your transit time is what? L by velocity, right? And velocity is mu times electric field. Now, electric field is basically between source and drain, right? The source and drain voltage we are changing. So the electric field is changing, then it makes sense to assume that the transit time will change. That's there in effect comes this effect of this immobile charges. Because what is happening is, because you have some immobile charges, even if there is a small change of this triangular potential, this triangular distribution, you will have some region where you are going to have only immobile charges. So and that immobile charge is highly resistive. That gives you a very high resistive zone. So any extra voltage that you are applying will drop across that small sliver that is getting exposed. So essentially, for all practical purposes, the amount of potential difference that the mobile charges are seeing remains the same. Right? So I didn't want to get into that because that goes slightly deeper into device physics, but that's what essentially happens. Okay. Okay. If you want to know more about this, meet me after class or come by my office, we can chat. So essentially, your IST can be broken down into regions of operation. One is it's 0 when VSG is lesser than threshold voltage. Then you have another region of operation where it's equal to mu P Cox W by L VSG minus threshold voltage times VSD minus half VSD squared. Then you have another region of operation where it's equal to half mu P Cox W by L VSG minus threshold voltage whole squared. Okay. So what are the boundary conditions? In this case, the boundary conditions is when VSD is less than VSG minus threshold voltage. And in the other case, the boundary condition is VSD is greater than VSG minus threshold voltage. Okay. So now, I mean, I hope that you will be able to relate these to some of the assignment problems that we are doing, where we didn't talk about the devices per se, but I gave you the IV characteristics, which look something similar to these, right? So in essence, you have already solved for this. So my job becomes easier. So So now let's concentrate on the Y parameters. Okay, because ultimately what we are planning to do is to make an amplifier where the incremental output and the incremental output should be related by a factor with more than one. That's all we are trying to do. And for that, we broken down everything into two incremental two-port networks. We wanted to get into, needed to find the Y parameters. Y11 and Y12 are 0, don't have to bother. But let's now delve into what's happening to, let's say, Y22 first, then we'll go back to Y21. So let's do Y22 first. Let's draw IST versus VST, and then we'll draw Y22. So this voltage here, where I hit, say, VSD is equal to VSG minus threshold voltage, where I say this VSG is equal to VSG1 because ultimately VSG is a parameter when I am sketching the ISD versus VSD plot. Okay. So if I only concentrate on this region of operation that is called a saturation region, what is the equation? This equation becomes half mu P C ox VSG minus threshold voltage whole square. Okay, VSG1 rather. Okay. So now can you comment on what will be Y21 graphically, for example, if I go from VSD equal to 0 to the saturation region of operation? What should it look like? High, low, 0, infinity. So let's concentrate here. What will be Y21 here? Or rather, I'm sorry, Y22, not Y21. Y22. Yeah. So Y22 will be 0 here, right? So Y22 will be 0 here, which is great because that's what we wanted, right? What will be Y22 somewhere where I am operating at VSD to be much lesser than VSG1 minus threshold voltage? It will be a straight line and the value will be mu P C ox W over L times VSG1 minus threshold voltage, right? And somewhere over here where I cannot really neglect the other term. So I have to differentiate this guy. So there your Y22 will be mu P C ox W over L VSG minus threshold voltage minus VSD. Okay, so from this also you can see that when VSD becomes equal to this critical voltage, your Y22 goes to 0, right? So now this critical voltage has multiple nomenclatures in the literature. This is also called the overdrive voltage. This VSG minus threshold voltage is also called overdrive. One of the reasons it's called overdrive or VOV is because you have to apply some voltage on top of threshold voltage to get mobile charges, right? So you are applying something on top of, over and above something. So that's why it's called overdrive voltage. This is also called that voltage for which you are getting saturation region of operation, right? When VSD becomes equal to your overdrive voltage, then you are getting saturation region of operation. So this is also sometimes called VD sat. In this course, we'll limit ourselves to VOV, but if you look into literature, sometimes you will see this VD sat being also used. So just don't get confused about this. So, but in this course, we'll be looking into, we'll be calling it V overdrive through and through. Okay. Another important nomenclature that you might find when you flip through textbooks is this critical voltage or this phenomena where the current gets saturated. I haven't yet named that. that region of operation, I mean, whenever this triangular channel gets pinned to the, whenever this charge profile gets pinned to this triangular profile, essentially that time we call it the pinch off has happened. The channel has gotten pinched off at the drain junction, right? So this is often also called pinch off region of operation. The saturation region is often also called, this is called, this is saturation region or called pinch off region. But in this course, again, we'll stick to saturation region of operation. This region of operation, where the current is almost linearly changing with respect to VSD, right? It's actually a parabola, but for very small value of VSD, it's almost linearly changing. So that is called a linear region of operation of the device, right? So this is called linear region. And this is also sometimes called triode region of operation, because these nomenclatures came from the days of cathode ray tube. So we borrowed the names. So linear region, triode region doesn't matter, but as long as we, in this course, we will limit ourselves to linear region of operation just to reduce the clutter. But I'm giving you all these names because you will look into books and you will see that sometimes it's called saturation region, sometimes pinch off region, sometimes triode region. There's a likelihood of getting confused. Just don't get confused. In this course, we'll be limiting ourselves to the terminology of saturation region and linear region. That's all. Okay. So this is good. So what is happening to Y21 then? This is Y22. What is happening to Y21? So Y21 in saturation region of operation will be, can you help me out? No, Y22 will be 0. Y21 will not be 0. Y21 is what? Del ISD, del VSG. It's a transconductance, right? We are affecting the current in one of the ports, that is between source and drain, by changing the voltage between source and gate, right? Yes, it will be mu P Cox is times W by L VSG minus threshold voltage. Okay. Okay, fine. So let's put the model together. Let's put the model together. So what does our incremental model for a MOSFET look like? When biased in saturation, this should be Y21 times VSG. Let's say we have to connect we have to call something a source. Let's say we call the top side source to match the figure. So let's say this side is a source, and as you see, this is a 3-terminal device, if I ignore the body. And we have always been talking about source to drain and source to gate, right? So essentially this other terminal gets shorted. And this becomes the gate, this becomes the drain. Right, so let's take this as source. This becomes the drain. So can you comment on the direction of the current source going towards the top, towards the bottom? Which side should I? Why should I put it at the bottom? I mean, both can be correct, but tell me. Okay. But what happens if I increase the source to gate voltage? If I increase source to gate voltage, I see that the current has increased, right? So that makes sense with respect to the normal device operation also, right? What is the normal device operation in saturation? If I increase source to gate voltage, the current between source to drain will also increase. So these two check out. Since this checks out, I can connect it. I can basically point the arrow in the direction that I have shown. Okay. Any questions? Okay. So now tell me what's going to happen. Let me go back to this picture once again. So tell me what's going to happen to this plot. Let me redraw. So for one particular value of VSG, I got this plot where this region is, or this point is VSG1 minus threshold voltage. Now let's say I increased VSG, right? So this is for VSG1. Let's say I increased VSG. I went from VSG1 to VSG2. What will this plot look like now? Intuitively, everything will increase. So when I say everything will, so at least we can start from the saturation region. Saturation region equation is simple because this is half half mu P C ox times WL, I missed here, right? You'll have W by L. Times VSG minus VTP whole square. So if I increase VSG, so naturally this plot is going to increase. What about in the linear region, somewhere here? Should it follow the same? Same plot for VSG1, or it will be increasing or decreasing? It will be increasing. So this will go like this. Now the only thing to bother about, where will it connect each other, right? Should it connect here, or should it connect somewhere here, or should it connect below the previous? It should connect to the right hand side, because ultimately
VSG2.
Yes, VSG2 is greater than VSG1. So VSG2 will be somewhere here. So ultimately you will go and maybe somewhere here it will get pinched off. Horrible drawing, but you get the idea. Okay. And quickly, before we stop, can you comment if VSG2 and VSG1 are not too far apart, right? Can you comment small signal wise, what is this difference of current in saturation region? So for example, I fix VSD, I check any particular value of VSD, let's say I call it VSDQ. I'm not changing VSD, and I have changed from VSG1 to VSG2, which means I see a current increase. What is that current increase? It should be Y21 times that delta VSD, right? I have not kept, I have changed, I have kept the output voltage constant. I have only changed input voltage. So change in current is essentially change in input voltage times some parameter. What is that parameter? Y2, right? So this change will be Y21 times VSG2 minus VSG1. Mind you, this is only valid as long as the difference is small. If the difference is large, you have to include those square terms and all. Okay. Okay, we'll stop here. Thank you.